Okay, this is your last video for chapter 20, acids and bases. I'm actually going to put 3 and 4 together. 3 is more theory, 4 is more math. It's hard to do one without the other. So I'm going to do 3 and 4 together. If you're doing 3 and 4, you're definitely honors right now. So, indicators. An indicator is just a weak acid that happens to change color when the H falls off. And we usually use the generic equation. I had a typo, but there you go, I fixed it, it's gone. H attached to the indicator is in equilibrium with H detached from the indicator, and there's a -1 charge there. So there's different indicators. Phenolphthalein we've used. Phenolphthalein is clear when it's an acid, when the H is attached rather, and red when the H is off. So usually we go for the in-between color, and we know that that's when it's half-half. And clear and red in chemistry land, halfway is pink. Then there's bromophenol blue. Use this one when you did a lab. There's dozens and dozens of indicators. I'm just throwing a couple out there. When the H is attached, it's yellow. When the H is unattached, it's blue. We usually like to get the color at equilibrium, so it's back to preschool. If you take yellow and blue, what do you make? Green. So we're just going for that middle color. So it actually shows 3 different colors, and this one shows 3 different colors. So it kind of tells me if I'm on the acid side of the world or the base side of the world, the acid side of the world or the base side of the world. And it kind of helps out like that. So that's what an indicator is. Helps me know what's going on without using real detailed electronics. Now, you're going to have to memorize these. Sorry. Strong acids. Strong means breaks up about 100%. Like it just breaks up. Same here. This strong also means the same. So if you have HCl and you put it in water, you know what you have? You actually have H and Cl. And look, one-sided arrow. That is an intentional one-sided arrow. I could do the same thing for HNO3, H2SO4. I'm going to give you a trick, and this is going to annoy you, but you're going to survive. H2SO4, the first H is strong. The second H is not. So one H falls off 100%. We'll talk about that one in AP Chemistry, okay? Come back. Strong base just means it breaks up. So which one should we do? Let's do sodium hydroxide. He's a favorite. Sodium hydroxide breaks up. One-sided arrow. 100% breaks up. No going back. There you go. Now this is going to bug you. When there's 2 H's, or it's a diprotic acid, remember that? The H's come off on one at a time. Watch this guy. He has 2 OH's. It is not a vocab word, but I'm just going to add it so your life is complete. This is a dibasic. Not a vocab word, just over-educating you. A dibasic, they actually both come off at the same time. What? Why is it not the same? I'm going to give you the complicated reason. That's like a molecule, and this is more like an ion. And ions break up 100%, and molecules break up a bit at a time. Not required. Not required, just trying to explain the world around you. Not required, just explaining the world around you. Okay? So memorize, those are strong and those are strong. Calculate the pH of. Okay, so let's do this. We're going to set up an old favorite known as the Rice chart. And you're going to put HCl. And you're going to decide, is HCl strong? Let me look back. And I'm going to have to say, yeah, he's on the strong list. So HCl strong, so he gets a one-sided arrow. And he's going to form H and Cl. I'm not giving you the right side, so you got to be able to do this. And it looks like it's starting with 0.25 molarity. They won't say initial, they're just going to tell you what it is. And it's for you to figure out the equilibrium. Well, we did not add any H and no Cl. Since he is strong, he will all break up. So minus 0.25. Because he's strong, it all breaks up. And if you start with 0.25 and 0.25 goes away, you end up with 0. And now I'm just working off of this. If 0.25 molarity HCl reacts, and the balanced equation says for every 1 HCl, you make 1 H. 0.25 times 1 divided by 1 is 0.25 molarity H. So I'm going to make 0.25 molarity. I will lose products and gain, I just lied to you. You will lose reactants and gain products. Okay? Another one off the change. If I lose 0.25 molarity HCl and it reacts in a 1-to-1 ratio, then I will gain 0.25 molarity Cl. If I start with none and I make 0.25, I will end with 0.25. If I start with none and I make 0.25, I will end with 0.25. The question asks for pH, which is based off this. pH is equal to the negative log of the concentration of H. So pH is equal to the negative log of 0.25. So I'm punch that in. It's going to be rough, but here we go. Negative log of 0.25 is my calculator's on scientific notation, 0.60. Whew, that is really acidic. That's not surprising. HCl is a strong acid. Okay, it's acidic. That confirms my thoughts. So rice charts, they're back. Have fun. All right, when you do a reaction, let's say it's an acid. Let me pick a weak acid, which literally means I'm picking an acid that's not on that list. I'm going to pick acetic acid. And if I break up acetic acid, and it's not on that list, it gets a double-sided arrow, which means I'm going to make an H and a C2H3O2. I would look up, because he's an acid, I would look up his Ka value. And I happen to know this one. It's ridiculous. I've accidentally memorized it. When I look him up, that's his Ka value. Since K is small, at equilibrium I have mostly reactants. And then if I wanted, I could do a rice chart depending on the problem. So K sub A just means the equilibrium expression constant of an acid. K sub B is the, and it probably would be better like this, just so you know. K sub B, I don't know if that's fonted the best, is the base dissociation constant. So you would look up, I'll pick NH3, and you see what he does. And this one kind of bugs because there's an extra H and OH, so it makes me want to write water on the left. That one's a tougher one. Since he's a base, I would look up the KB in a chart, and there'd be some sort of number, and then I could do a problem with it. So how about we try a problem so that it's not all theory and it's got some numbers. Most of you like numbers. So for a solution of 0.1 molarity, this is actually formic acid. I don't know that you need to know that. Extra information. If you ever get stung by a red ant, well, that's the thing that hurts. At equilibrium has an H plus concentration of 4.2 times 10 to the minus 3. Calculate Ka. So here we go. I'm going to set up a rice chart. I'm going to write the reaction. got my acid, HCOO minus plus an H plus. And this is one of those things you just learn when you're in chemistry a long time. If you see a COOH, the last H is acidic. So I'm going to say that again. If you see COOH, the last H is acidic, and it's actually monoprotic. Only one H will fall off, even though there's probably more there. Okay, and I want to figure out the Ka for this equation. That's my question. I know I'm starting with 0.1 molarity of formic acid, and it's going to look like that, so you just have to realize that's initial. Sorry. And it did not talk about either of the products in the beginning. But it does say at equilibrium, BAP. I know the H here is 4.2 times 10 to the minus 3. So if I start with 0 and I went up to that, I must have gone up 4.2 times 10 to the minus 3. Now I'm going to use this down here. If I had 4.2 times 10 to the minus 3, H plus, I'm going to change H plus, I'm just going to go here, into HCOOH. For every, it's a 1-to-1 ratio, for every 1 H plus, there's 1 HCOO minus. And it's going to equal the same thing. If you can eyeball it, you don't have to do this. I like to do it. I'm not as smart as you. There we go. So if I make that much of this, I'm also going to make this. How much of this is going to go away? Let's make another one. I'm going to work off that. 4.2 times 10 to the minus 3. Hydrogen ion. For every 1 hydrogen, there's 1 formic acid. Pull out your calculator. Figure it out. Oops, I almost miswrote it. Sorry. Since these are made, this is lost. So this I'm going to do my calculator. So if I have, and I have sig fig issues, I'm fully aware. I'm just trying to get you through the material. 0.1 minus, that's for Kelsey, in case Kelsey's watching this video. If Kelsey probably doesn't need to watch the video, tell her my sig figs are wrong. Tease her a little. Okay, so I've got 0.0958 molarity. This minus that equaled that. This plus that, I can do in my head. I still haven't answered my question. My question is Ka. And Ka is going to equal products raised to the coefficient power. Oh, run out of room. Sorry, guys. Divided by reactants. Raised to the coefficient power. I've got some calculating to do. Oops. There we go, divided by 0.0958. You know what? Sometimes it's nice to do the math twice, because you saw how I punched the stuff in wrong. So let me do it one more time. Ah, good. That's actually the answer to the question. So rice with acid bases. You're so ready for AP chemistry. Next, last problem of the chapter. Here we go. Monoprotic weak acid. Okay, so 1H comes off, double-sided arrow. At equilibrium gives me what is the pH of the solution. I'm checking that the numbers are different from the last one, and they are. So I'm going to start with a rice chart. So RICE. You can try and sneak, but I'm still going to say your name, James. Now everyone knows you snuck in the room. You can't shush your mom. Good night. Okay, so weak acid. I have no idea what it is. So I'm just going to put an H attached to something. and then the H will fall off, and the something will be left over. Isn't that a lazy way? I love it. Okay, so I'm starting with 0.2 molarity. I added no H or A minus. At equilibrium, I'm going to have 9.86 times 10 to the minus 4 of the H. And that's all I know. So I feel like I've, at least in Gaines's class, you've earned a point because you set up a rice jar and you put chunk in it. You haven't done any chemistry, by the way. All right, the pH. Actually, I didn't need a rice chart for this, so that's all right. pH is the negative log of the H. I'm just going to plug that in there. And pH equals, here we go, negative log 9.86 times 10 to the negative 4th. I like it when the numbers are nice and clean. 3.0. So there's my pH. Well, apparently I need rice down here. That's all right. It happens on test 2. You start a problem and you realize you didn't need to do it. Calculate the Ka. So now for the Ka, I'm going to need all of these concentrations to get my Ka. So now I have work. If I start with none and I have this, then I've gone up that amount. If I went up, okay, I'm doing my change stuff down here. If I went 9.86 times 10 to the minus 4th of the H, and the H and the A react in a 1-to-1 ratio, I'm just proving what some of you already have in your head. If the coefficients are 1, these are really easy. If the coefficients are not 1, it's kind of a bugger. All right, now I'm going to do HA. If I produce this much H, and the H and the HA react in a 1-to-1 ratio, then I would lose 9.86 times 10 to the minus 4th HA. If I start with 0.2 and I lose this, calculator time, Kelsey, sig fig error, I'm fully aware. Minus 9.86 times 10 to the minus 4th. I get what point? Let's get out of scientific. 0.199. If I start with 0 and I make that much, I'm going to end with that much. We're pretty good. I just feel like we're pajumbled here. So my Ka is going to equal the concentration of the products raised to the coefficient power, boop, times the other product raised to the coefficient power, boop, divided by the reactants raised to the coefficient power. I just have to do a big math problem. Here goes. 10.86 times 10 to the minus 4 times 9.86 times 10 to the minus 4 divided by 0.199. I believe Ka is, I'm going back to scientific because I'm too lazy to count my zeros, 4.9-ish to the negative 6. It's a lot of math, so I'm going to do it one more time. Okay, I like it. Put a box around it. That is chapter 20. Hope that helps.